Hello everybody, welcome into another lesson. So today we're going to talk about the area of parallelograms, triangles, and rhombuses. So up first here we have the area of a parallelogram. The area of a parallelogram is similar to that of a rectangle. You just take the base, the length of the base, times the length of the height, and that will give you the area of a parallelogram. But here's the thing with parallelograms. The base is the same. It's either the top side or the bottom side is the length of your base. But the height can only be a straight line, or in this case, the height would actually be the altitude of the parallelogram that goes down from the top base to the bottom base and forms a perpendicular line to the base. The slanted sides of the parallelogram cannot be your height. Your height has to stand straight up. Think of it like when you go to get your height measured at the doctor's office. They're not going to take your height with you slanted over. No, they're going to take it with you standing straight up against the wall. Well, that's how you can remember the height. So let's do some examples here for area of a parallelogram. So I will draw said parallelogram. All right. So let's see what we got here. I guess we might as well label the opposite sides too, because opposite sides of a parallelogram are congruent. Actually, let's do this here. This is a 60-degree angle. All right. So here we have a parallelogram with two sides have length 6, which are your bases, and then the sides have a length of 3. Well, we have a 60-degree angle here. We don't know the height, do we? That's okay. That's quite all right. We can get the height. How do we do that? You draw the altitude from the top base to the bottom base. That's going to be your height. Just draw a auxiliary line there, which in turn will form a right triangle to the left side there where the 60-degree angle is. Now, when you have a right triangle, you have a 30, 60, 90 right triangle, don't you? Well, that means because this angle has to be 30, so what is true of a 30, 60, 90 right triangle? That the side opposite the 30-degree side is half the length of the hypotenuse, which is 3. So this would have to have a length of 1.5 here, which means the height, which is the side opposite the 60-degree angle, is going to be 1.5 times the square root of 3. So now we found the height of the parallelogram. It's going to be 1.5 times the square root of 3. Now we may figure out what our area is. The area, of course, is equal to that base, which has length of 6, times your height, which would be 1.5 times the square root of 3. Which we're going to approximate the area to the nearest tenth. So we're just going to put all this into the calculator and we'll get a decimal approximation. So let me go to my handy dandy calculator on my smartphone. It would give me about 15.6. So the area of this parallelogram is approximately going to be 15.6 square units when you multiply the base and the height. And I got a few more examples for parallelograms. All right. So we got our parallel markers set up. This has a length of 12. This has a length of 8. This angle here is 50 degrees. So interesting. We have here, again, we have what I would say first, we clearly see this as a parallelogram because you have a quadrilateral with both pairs of opposite sides parallel to each other. Thus, that's the definition of a parallelogram. And now we can label the opposite sides because opposite sides of a parallelogram are congruent. Okay, so you have the length of your base being 12, but we don't know the height, which is what you need to find the area. So that height, you're just going to draw an auxiliary line here, which will be the altitude of this parallelogram, which will be perpendicular to the base. Now, we're trying to solve ultimately for the height, aren't we? We need to find the height before we can find the area. Well, you have a 50-degree angle in this right triangle, so it's not a straightforward 30 or 60, 90 right triangle, and you don't know the length of this leg of the right triangle, so we're going to have to use some trigonometry. If we have the opposite leg and the hypotenuse, what ratio is that? That's going to be the sine ratio. So you would set up the sine of 50 degrees would be equal to the height, which is h, over the hypotenuse, 8. Which that means the height is equal to 8 times the sine of 50 degrees, which would mean the height is approximately equal to, we're going to take this to the nearest tenth. So again, make sure your calculator is set to degree mode. 8 times the sine of 50 degrees is approximately 6.1. So the height of this parallelogram is approximately 6.1. Now we can proceed to find the area. The area, of course, is equal to the length of that base, which is going to be 12 times your height, which is approximately 6.1. And then the area is also going to be an approximation to the nearest tenth instead of an exact because the height was approximated. So let's take 12 times 6.1. It should definitely be over 72. 73.2. All right, so the area of this parallelogram is approximately 73.2 square units. So yes, sometimes you can actually involve some trig in this too. All right. Let's go back here. Let's see, then we have another parallelogram here. This parallelogram has side lengths of 6 and 10. We'll make the base 10, we'll make the lengths of this side 6. So this base would be 10. This length would be 6. and then we have a 45-degree angle here in the parallelogram. We need to find the area. Well, we know the length of the base to be 10, right? What we don't know is the length of the height, which again, set yourself up in an auxiliary line here, which will be perpendicular to the base, which would be the altitude. And then you now have yourself a 45, 45, 90 right triangle. So we can find the length of the height. So we have the hypotenuse of this right triangle that has a length of 6. What is the length of a leg of a 45, 45, 90 right triangle? It's the hypotenuse divided by the square root of 2. So that means the height is equal to the length of the hypotenuse, 6, divided by the square root of 2. Of course, you're going to want to rationalize the denominator. Well, no, you don't really need to, because we're just going to do a decimal approximation. If you were asked to write it exactly, you would rationalize it, but I don't think that's necessary in this case. We're going to just do a decimal approximation to the nearest tenth, which would give you about 4.2. So the height is equal to 4.2 for your parallelogram. Now you can go ahead and you can find the area of this parallelogram where you have the length of the base being 10 and the height of it being 4.2. Which will give you an approximation of about 42 square units would be your area for this parallelogram, approximately 42 square units. And I think that's good for parallelograms. Now let's talk about some triangles. We'll deal with triangles next. I'm going to draw a few different examples to illustrate this point. And talk about them. Alright, so the area of a triangle is equal to half the length of the base times the height. Now, of course, we have a right triangle here first. In a right triangle, it's real easy because your height is just the length of the leg that stands straight up. That's perpendicular to the base, so that makes that real easy. But if you have an acute or an obtuse triangle, it's a little bit different. In either case, in the acute triangle, the bottom side that lays straight down, of course, is your base. But much like the parallelogram, your height cannot be these slanted sides. Your height would have to come from the top vertex and form a perpendicular line all the way down to the base. That would be your true height. And then in an obtuse triangle, you would have the length of your base. But again, these slanted sides are not your height. What you would do for an obtuse triangle is you're going to have to draw your height actually outside of the triangle, coming from the top vertex down to the point where it would meet an auxiliary line extending from the base and be perpendicular to that. And the auxiliary line would not count as the length of your base, only that of the original triangle would. So those are your three cases for triangles when trying to find the height. Now let's get into some area of triangle problems. All right, what's the first one? This one's not going to be bad at all, because this here is an equilateral triangle. We want to find the area of this equilateral triangle. Well, an equilateral triangle also means what? That it's equiangular. Which means you have, in fact, 360-degree angles. So that would be 60. Well, we have the base length of 4, but you still need to find your height. So go ahead and draw your auxiliary altitude line from the top vertex down to the base. And then you'll have this split into two right triangles, which this would be your height here, is that auxiliary line. Now you have a 30, 60, 90 right triangle you can use to solve for the height. So what is, now we have the hypotenuse here of 4, right? This angle up here is clearly a 30-degree angle. The leg opposite the 30-degree angle is always half of the hypotenuse, so that would have to be 2. This leg would have to be 2. And then the height, which is the longer leg, since it's opposite the 60-degree side, your height is the square root of 3 times the shorter leg, so your height is equal to 2 times the square root of 3. I'm going to keep that intact for a minute because we want to get a decimal approximation in the end, of course, but I'd like to get it as close to exact as possible. Since we know the height now, we can find the area. The area is equal to 1/2 of the length of the base, which is 4, times your height, which is going to be equal to 2 times the square root of 3. Which can simplify into 2 times the square root of 3, which would be equal to 4 times the square root of 3. So now we can just run a decimal approximation here and find the area of the triangle to the nearest tenth. Alright, so take 4 times the square root of 3. That's going to give you about 6.9. So the area of this triangle is approximately equal to 6.9 square units. Another interesting triangle, but it's a little bit different this time. They give us that the length of the whole base is 6, they give us that the other two sides have a length of 5. We don't know the height, though. That's one thing we don't know. But nonetheless, let's go ahead and draw our altitude. Let's form our two right triangles from this. So, here is the thing. Let's look at the whole triangle overall here, right? The whole triangle, well, actually, we don't even got to do that. I'll tell you why. Because you have this split into two right triangles, well, the hypotenuse of both right triangles are congruent, and one of the legs certainly is, right? Because they both share this leg. So each two right triangles here are congruent to each other, which means both parts of the base are congruent to each other, which means they would both have to have a length of 3. So now we can easily ascertain the height. What we have to do here to find the height, just use Pythagorean theorem. So you'll take your height squared plus the length of your other side here, which would be 3 squared. Set that equal to the length of your hypotenuse squared, which would be 5 squared. So then you get h squared plus 9 equals 25, which would give you that h squared equals 16, which would give you a height of 4. So we found the height to be 4 units. Now we can find the area of the triangle. The area of the triangle is going to be equal to half times 6 times the height of 4. Which, when we do that, what's half of 6? That's 3, then times 4 is 12. So the area of the triangle, therefore, is going to be 12 square units. So yes, Pythagorean theorem and trigonometry can very heavily be involved in this. What's next? Got 2 more triangles here. Then we'll move on to rhombuses. And good news is both of these are considered right triangles. Alright, they give us a length of the base to be 10. They give us this angle here to be 20 degrees. So before we can even attempt to find the area of this triangle, we need to find the height, don't we? So this would be the height since it stands straight up on the right triangle. So at least we don't have to draw auxiliary lines. That makes our lives a little bit easier. Now, you're trying to find the opposite side over the adjacent side. When you have opposite over adjacent, that's the tangent ratio. So you'll take your tangent of 20 degrees, set that equal to your opposite side, which is the height, divide that by the adjacent side, which is 10, which would mean your height is equal to 10 times the tangent of 20 degrees. And then now we can get a decimal approximation to 1 decimal place for the height. Again, make sure your calculator's in degree mode and not in radian mode. It's going to make a big difference. So 10 times the tangent of 20 degrees, to the nearest tenth, it's about 3.6. So the height of your right triangle here is approximately 3.6 units. Now then again, we're going to take the area to find that. That's going to be equal to half the length of the base, which would be 10, times 3.6. Which would ultimately give you 5 times 3.6, which the area itself is going to be an approximation to the nearest tenth because the height was approximated. It's going to be pretty much impossible to get an exact area, but we can get an approximation. That gives us, well, actually, that would give us 18. So the area is going to be approximately 18 square units for that triangle. One more triangle, then we can move on to rhombuses. Good one. So this time we have a right triangle where the hypotenuse is given to us to be the length of 12, but we don't know the height, which would be this side here, right? It'd be this leg. And for one, we also don't know the base. You would actually need to know both the base and the height. So it don't matter which one you want to start with. We need to find, I'm going to start with the height. Height is obviously the adjacent leg to the 54-degree angle, then you have the hypotenuse. If you're setting up an adjacent and hypotenuse ratio, that's going to be your cosine. So you set up your cosine of 54-degree ratio, that's going to equal your adjacent length of h divided by your hypotenuse, which is 12. So the height is going to be equal to 12 times the cosine of 54 degrees, which now will get a decimal approximation to about 1 decimal place. What is 12 times the cosine of 54 degrees? It's about 7.1. So the height is approximately 7.1 units, okay? Now we need to find the base. Well, the base is clearly the opposite side from the 54-degree angle. Then you know the length of the hypotenuse. So if you have opposite over hypotenuse, that's the sine ratio. So you'll set up your sine of 54 degrees, set that equal to your base over the length of the hypotenuse of 12. Now your base is equal to 12 times the sine of 54 degrees, which then will get a 1 decimal place approximation for the length of your base. So let's go ahead and figure that out. So 12 times the sine of 54, nope, that's the wrong number, gives you about 9.7. So the length of your base is approximately equal to 9.7 units. Now we can go ahead and find the area since we know both the base and height. The area, I'm actually already going to say it's approximately equal to 1/2 times the length of that base, which is 9.7, times the length of your height, which is 7.1. Which means your area is also going to be a decimal approximation since your base and your heights were also. So let's go ahead and do that. You get about 34.4. So the area of this triangle is approximately equal to 34.4 square units. Alright, now we can move on to the final thing we're here to learn today, which is about rhombuses. We can find the area of a rhombus. let's do this then here, because I need to illustrate this point. Alright, so a rhombus, of course, if you remember, is an equilateral parallelogram that may or may not have right angles. A general rhombus has obtuse and acute angles, where a square is a special type of rhombus that has all right angles. Well, to find the area of a rhombus, it's just half the length of the first diagonal times the length of the second diagonal, which means you could actually apply this to squares also. Since a square is a rhombus, you could actually, in theory, do that. So that is something to keep in mind. Now, of course, we're going to get to some rhombus problems. Well, let's go ahead and do that here. Not the straightest I've ever done, but you get the idea. All right. Draw this diagonal as clearly as I can. Alright, now let's see what they give us for this particular one. Okay, so do we notice something here? I also put a perpendicular marker where the diagonals intersect. If we remember, the diagonals of any parallelogram not only bisect each other, but the diagonals of a rhombus are also perpendicular to each other. So if there were certain lengths you didn't know, you could separate these into right triangles, which we're going to have some problems like that today with some rhombuses. But we have the length of all four sides of the rhombus, which of course they'd all be congruent to each other. We even have the lengths of each segment of the diagonal. We'll call this purple diagonal here, the length of diagonal 1, of course, is equal to 2 plus 2, which would mean the length of diagonal 1 has a length of 4, right? Now, in order to find diagonal 2, actually let me put that with its appropriate color. Diagonal 2 is this blue diagonal. Each segment of the diagonal has a length of 5, so that's equal to 5 plus 5. That means the length of the second diagonal has a length of 10 units. Now we know the length of both diagonals, we can proceed to find our area. The area is equal to 1/2 of the length of your first diagonal, which is 4, times the length of your second diagonal, which is 10. Which then means, of course, you take half times 4, what is that? That's 2 times 10, which is 20. So the area of this rhombus would be 20 square units. That's exactly what you would get, is 20 square units. So that wasn't too bad. All right, what's next? There's another rhombus. What do they give us this time? Boy, they sure love their lengths of 5. They sure do love their lengths of 5 for the sides. Well, that's fine. Whatever floats their boat, right? This is a little bit different, though. Very different. Let me set up the length of the first diagonal here. Then let's set up our second diagonal. And of course, for good measure, let's place a perpendicular marker here for the diagonals intersecting. Since the diagonals of a rhombus are in fact perpendicular, that means you have 4 right triangles here inside the rhombus. Now, they also give you that this diagonal in blue, your first diagonal, each segment has a length of 4. Which means now that we need to find the length of at least one segment of the purple diagonal. Well, what do we know? You have 4 right triangles, right? Which means this 5 is the length of your hypotenuse. Well, let's call this length here for this leg D. So, of course, now it's just a matter of doing some Pythagorean theorem. If you take that D squared plus the other leg 4 squared, set it equal to your hypotenuse 5 squared, you'll get that D squared plus 16 is equal to 25. Which then means that D squared equals 9, so that would give you D equals 3. Now, that D equals 3, that's only half of this diagonal. We know the diagonals of a rhombus bisect each other, so the length of this other part of the diagonal is also 3. Now we have officially come up with the length of both of our diagonals. Let's start with diagonal 2 here, which I'll call the purple one. That, of course, is equal to 3 plus 3, which means diagonal 2 has a length of 6. The blue diagonal has segments 4 and 4, so the length of diagonal 1 is equal to 4 plus 4, which would equal 8. Now that we know the length of both diagonals, we can proceed to find the area. So the area of this rhombus is going to be equal to half of the first diagonal with length 8 times the length of your second diagonal with length 6. Well, what is half of 8? That's 4, then times 6 is 24. So the area of this rhombus is about, or is exactly in this case, 24 square units. Got a couple more rhombus problems. I think they're good ones though, because I don't think anyone's had exposure to the area of a rhombus until this course. It wasn't really covered in previous courses, so this is a good one to cover. No, we already did that kind. Yep, we got 2 more. Two more I'm going to do today. That's definitely not good. Let's extend that a little bit here. All right. So they give us here, in this particular case, that this rhombus has side lengths of 6 centimeters, so we actually have units this time. This rhombus has side lengths of 6 centimeters. What do they give us also? They give us that you have a 120-degree angle. Well, if we have a 120-degree angle, we don't know the length of any diagonals, but that's okay. That's quite all right. Because, what does that mean? That has to mean then, since opposite angles of a parallelogram are congruent, that means the other angles are supplementary to it. So this angle here would be 60. Now, what we're going to have here, you want to make your diagonals in such a way, your diagonals of this rhombus actually bisect each other too. The diagonals of the rhombus, well, they bisect each other, but they also bisect the angles. So we're going to create our diagonals where they bisect the angles. So what do you have here? If you have a 120-degree angle here, if you've bisected that, what is it? That's a 60-degree angle. Right? And then that means all that's left here is also a 60-degree angle, which is going to give you what? What does that give you then? You have both sides, you have two sides of this equilateral triangle here with 6 centimeters. That means diagonal 1 in purple, being the third side, since it's an equilateral triangle, would also have to have a length of 6 centimeters. So we got the length of diagonal 1, right? Now, there's a good reason why I'm about to do this. I'm going to erase this for a very good reason. Because we're about to start working on the other diagonal. We need to know the diagonals, of course, in order to get the area of this thing. So let's go ahead and do that. We at least got our first diagonal dealt with. What does that obviously leave here then? The other diagonal would have to go from each 60-degree angle. Well, now this is where it gets interesting. You have two 120-degree triangles, but we need to find the length of the we need to find the length of this diagonal here. I actually probably should have kept this, because this diagonal, since the diagonals are perpendicular, what would be true? What is true then? That you have now right angles. Of course, each part of this purple diagonal has length of 3. You have a 30, 60, 90 right triangle now. We can find one of the lengths here of the blue diagonal, the second diagonal, which would give you the length of the other part too. I should have kept it then. My apologies, folks. But if we bisect the 120-degree angle, you have a 60-degree angle. If you bisect the 60-degree angle, you have a 30-degree angle. So this is a 30, 60, 90 right triangle. So this would line up too with this leg of the right triangle being 3, because this would be a 30-degree angle down here. And then you have the length of your hypotenuse being 6, which is twice the length of your 30-degree leg. Well, what is the length of the leg opposite the 60-degree angle here? It's actually going to be the square root of 3 times the shorter leg. So each part of the blue diagonal is actually going to be 3 times the square root of 3 centimeters. So your diagonal 2 is equal to 3 times the square root of 3 centimeters plus 3 times the square root of 3 centimeters, which means that it's going to be equal to 6 times the square root of 3 centimeters. And now we can find the area, which ultimately we're going to do a decimal approximation, of course. So the area is equal to 1/2 of the length of your first diagonal, which is 6 centimeters, times the length of your second diagonal, which is 6 times the square root of 3 centimeters, excuse me. Well, what is 1/2 times 6? That's 3. 3 times 6 is 18, so the area is exactly 18 times the square root of 3 square centimeters. Since you're dealing with area, now we want to find a decimal approximation for that to 1 decimal place. Let's take 18 times the square root of 3. (18 times the square root of 3 would give you about 31.2. So the area of this rhombus, therefore, is approximately 31.2 square centimeters. And then I just have one more exercise left for rhombuses, then we're done with the lesson. All right, let's do this. I apologize if this last one's not drawn to scale the best, but let me tell you what they give you here. They give you that the perimeter is equal to 68. So the perimeter of this rhombus is 68 units. So to find the length of each side of the rhombus, you just take 68 divided by 4, which should give you 17. So each side of the rhombus has length 17. So there's some missing information we can use. They even give you that the length of one diagonal is 30. So that's pretty bad. The length of one diagonal here is 30, which I'm going to split it into 2 segments. That means that diagonal is actually going to have a length of 15 then. We're actually about to get into some trig here. Maybe. No, more like Pythagorean theorem, actually. We're about to use Pythagorean theorem. So if this diagonal is a length of 30, that means each segment here has a length of 15. And of course, you have 4 right triangles now. That's going to make your life a lot easier. We know the length of one diagonal. The length of this blue diagonal is 15 plus 15, which would give you what? They would have a length of 30. So that's not so bad. Now we just need to use some Pythagorean theorem to find even 1/2 of this diagonal. So you're going to, of course, set up your Pythagorean theorem. We'll call this length d. So we'll take d squared plus your 15 squared, set that equal to the length of the hypotenuse, which is 17 squared, which would give you d squared plus 225 equals 289, which would then give you what? D squared equals 64. So the length of D, of course, is going to be 8. So this half here of the purple diagonal has a length of 8. Which means the other half, since diagonals of any parallelogram are bisected, this half is also 8. So now we know the length of diagonal 2, it's equal to 8 plus 8, which is 16. Alright, now since we know the length of both diagonals, we can proceed to find the area. The area, of course, is equal to half the length of the first diagonal, which was 30, times the length of your second diagonal, which is 16. Which, if we take that, that's going to end up being 240. So the area would be equal to 240 square units once you do the math. The area of this rhombus would be 240 square units. So that's it for the areas of parallelograms, triangles, and rhombuses. The very next lesson we are going to move on to the area of trapezoids. So I hope everyone has a good night. Take care.